Okay, so let us start with the topic of Venn diagrams today. These diagrams are ways of representing sets pictorially as pictures or figures. And the idea was given by the English mathematician, logician and philosopher John Venn, who lived in this time period. Unfortunately, the year of his death is given wrong in the text. This is really, what can I say about this? The text, NCERT, I don't know about the other subjects, but in mathematics it's full of all kinds of errors, mathematical errors and errors of that kind. Okay, page numbers are wrong, grammatical mistakes, answers are wrong, all sorts of errors are there. But anyway, let's just continue our discussion. So what we have in these diagrams are some figures of closed regions, regions bounded by closed curves, and these regions help us enclose the elements of a set. For example, consider these two sets U and A. U consists of all the positive integers or natural numbers less than or equal to 10, and A consists of those numbers in U which are even. So A actually is a subset of U. To represent these two sets pictorially, first we draw a rectangle. You may remember that in the previous video we said towards the end of our discussion that when we represent sets as Venn diagrams, then universal sets usually are represented by rectangular or square regions. So in the discussion where these two sets are the only things we are discussing about, you can think of U as the universal set because A is a subset of U. In other words, your ingredients of discussion are all within U. So U is a universal set, and that's why it is expressed by drawing this rectangle. And how do you represent the elements geometrically, pictorially? By drawing dots, one dot for each element within that region which is representing that set. So each dot representing these elements in U are to be drawn inside this rectangle, not outside, also not on the actual rectangle itself. Of course, when you say the geometric figure rectangle, it really just means the collection of all the points which lie on these four line segments. That is the rectangle, not the region bounded by it. Okay, that is the interior of the rectangle. So when you draw these points representing the elements of U, you draw them in the interior of the rectangular region. Okay, so that is U. And inside U, you have the subset A, which we can represent by a closed region like this, a region bounded within a closed curve. Now here's the thing, that closed curve usually is drawn as a circle or an ellipse, but of course that is not necessary. You can draw an irregular curve like this also. The only condition is that it should be closed. Okay, it should not be open. It should be closed and it should bound a region within it. Just like you have drawn the points of U in the interior of the rectangular region, here also the points of A have to be drawn as dots in the interior of this region which is representing A. Note that we have carefully drawn these dots and labeled them with the names of the elements that they are representing. For example, here beside this dot we have written 1, which means that this dot represents the element 1 pictorially. However, note that this dot representing 1 has been drawn in such a way that it is inside U but outside A. That's because 1 is not an element in A, but it's an element in U. However, the dots representing the elements of A have been drawn within the region representing A, of course, so that they are not just elements of A, but they are at the same time within the rectangular region also. That's because besides being elements of A, they are also elements of U. However, that is not the case with this element, say 3. 3 is an element in U, but 3 is not an element in A because 3 is odd. Okay, so that's how we pictorially represent sets. Now, what is the advantage of such a representation? You see, of course, looking at these sets also, you know what its elements are. However, when you look at a figure like this, you see all the things at once. Okay, so that is the advantage. One more thing that I should add here is that it does not really matter. Say you consider the element 1. You have to draw a dot in the interior of U which will represent 1, but where? Where exactly in the region should you draw that point? That does not matter. In anywhere you can draw. The only thing you should keep in mind that it should not lie on this curve. Also, it should not lie in the region bounded by this curve which is representing A. Instead of drawing it here, I could have drawn it here also. That is also the Venn diagram for U. Okay, it does not really matter exactly where you draw the dot. Now, if you introduce another set, say this set B, U and A are as before, so that the diagram also accordingly is essentially as before, although here, for example, you see 1 here and you see 1 here, but as I have told just now, you can draw 1 anywhere, keeping in mind that it should not come here or on this curve or on the actual rectangle itself. It should be in the interior. Similarly, the dots representing the elements of A have also been drawn accordingly, but now we have a new set B. So that's why that set B, which consists of 4 and 6, have been drawn separately. See, I am also abusing the language. I have just now said that set B is drawn. A set is never drawn, but the pictorial representation of the set is drawn. Okay. So that is drawn like this, so that the element 4, for example, is now an element in B, but at the same time it's within this larger region also because it's also in A, and it's at the same time within this rectangular region because it's after all an element of U. Alright. So besides these things, what else is there to say? Oh yes. Where do you write these letters though? The letters, the set names. That you write just beside that region, outside that region. Okay. Where, exactly where again, you write, whether you write, for example, here we have written U on top right corner. Here bottom right corner. That does not matter. It should be somewhat close to the region. Similarly, here A has been written just beside this region, outside the region. And just like that, B also, in that second case. Okay, so these are Venn diagrams. Next comes the topic of operations on sets. Operations on sets. That is the next thing. Now, what do we mean by an operation? We will discuss a little bit about that. And the discussion will be based on an example of an operation with which we are already familiar. We know that. And so that discussion basically is just this. We have been familiar with 4 very fundamental operations for a very long time, okay? And those operations are the operations of addition, subtraction, multiplication and division on numbers. Here the word numbers means you can say real numbers, okay? Now, what is the common characteristic of these 4 operations? The operations are entirely different, okay, from one another. We know that when we, for example, add 2 numbers, 2 and 3 say, we get 5. However, you change the operation, say you multiply 2 and 3, you get 6. And then you subtract or divide 2 by 3, you get other numbers. But the characteristic that is common to all these operations is that you give the operation is like a machine in which you put 2 things and it gives you 1 thing. In the addition operation machine, you put 2 and 3 as your ingredient and it gives out the product 5. In the multiplication operation machine also, you put 2 things, 2 and 3, and it gives you 6. Because of this, and that is also the case with subtraction and division, because of this type of operations are called binary operation. Binary operations, where you give 2 inputs and 1 output is given back to you. Now, such binary operations on numbers have their counterparts in sets also. Here, the inputs are numbers. Now, the inputs of these new operations that we are now going to discuss will be sets. So, the first such binary operation on sets is union of sets. And the idea will be motivated like this. Let A and B be 2 sets. Think of the situation here, let 2 and 3 be 2 numbers. Then we say that 2 plus 3 means this. Okay, so just like that, the union of A and B, correspondingly here you would say the sum of 2 and 3 is so and so things, is. What do you get here? You get back a number again. Okay, adding 2 numbers, you get back a number, an object of the similar type. The inputs were numbers, the output is also a number. So accordingly, here the inputs are sets, the output should also be a set. I mean, it's that kind of operation. We are analogously defining something new now. Is, so we write this set. But what set is it? It is the set of all the elements of A together with all the elements of B. So we combine the 2 sets in some sense. it's like having two bags of some items, emptying both the bags on your bed or say on the floor, and you take all the items, mix them up. Mix them up means you just take all of them together and put all those items, both from bag A and bag B, say I call the two bags A and B, into a new bag. Then you get a new set of items. That is the union of A and B. All the elements of A together with all the elements of B. Have we written? Yeah, the union of A and B is the set of all the elements of A together with all the elements of B. It's a combination. This set is, okay, perhaps the other things associated with this definition I should write afterwards. Okay, let us first do something else. We understood the basic meaning. You have two sets, you take all the elements of the first set with all the elements of the second set, mix them together and you get a larger set naturally. That set is the union of A and B. So let us now illustrate first this idea with some examples. And the examples that are there in the text are these. Yes, see, I am not going to maintain example numbers or definition numbers, these things, okay, because the ideas are what matter. So I am just going to write simply example. Let A be the set whose elements are 2, 4, 6 and 8. These four natural numbers. And B be the set of, I was going to write in words, B is the set of these numbers 6, 8, 10, 12. Now, unlike the real world example of items in bags, in sets, however, you can have the same element in two sets. That is possible. That, however, is not possible with two bags. Say, if you have one item in one bag, it cannot simultaneously be in the other bag as well. But for sets, we have that situation. For example, 6 is an element in A as well as in B. So when you mix them together, you should think that 2 6s come, but those 2 6s are counted as only 1, because actually there are not 2 6s, it's only that these numbers are scattered on the floor. You consider A to be the set of these numbers and at the same time you consider B to be the set of these numbers. And there are two common numbers, 6 and 8. That's the thing. Actually, they are not repeated. Then, and as a result, while writing the union in roster form here in this case, we will also not repeat elements. Then the union of A and B is the set this 2, 4, 6, 8, 10, 12. Note that the decision of not writing 6 twice matches with what we have already discussed about the roster notation. In a set, while we write it in roster notation, in roster form, no element is repeated. Repetition is allowed, but it does not serve any purpose. If anything, it just takes more effort to write without any, it doesn't give us anything useful. So that's why repetition is not encouraged. So that thing has matched. And one more thing is that, again, here the order in which you write these elements in fact does not matter. Although here it seems that we have chosen the increasing order in order to write these elements 2, 4, 6, 8, then 6, 8, 10, 12. Here also the union has been written in the increasing order, but you already know that order does not matter. You could have written 12 first, followed by 2, and then 6, 8, in any way you can write. So this is the union of A and B. Let's take another example. Let this time A be the set of all the vowels in the English alphabet, that is A, E, I, O and U, and let B be the set of only these three vowels A, I and U. Well, in this case, it turns out that B is a subset of A. All the elements in B are also in A. But that's not a problem. We can still form the union of A and B. So, what shall we get? If we collect all the elements of A together with all the elements of B, in this case, unlike the previous case, we do not get anything new from B. You see, in the previous case, we had 2, 4, 6 and 8 in A. And then when you consider the elements of B along with the elements of A, 6 and 8 were already present in A. But the new elements 10 and 12 came and increased the size of A. It became a larger set. Here, however, when you similarly argue, you do not get anything new. You get back A itself. The union of A and B is, without thinking of that first, let us simply write the set in roster form. The elements of A are what? A, E, I, O, U. And then the elements of B are A, but that is already there. I is also already there and U is also already there. So we don't get anything new, and this is the union. I.e., the union is nothing but A. And this gives you an idea of a general situation. Namely, that if you take two sets A and B, such that B is a subset of A, so that the elements in B are already there in A, then the union of A and B will be A, always, not just in this case, because of that. Because of the definition of union. And let us take another example. In this example, in a school, there is a football team and there is a hockey team. In the football team, there are 3 students from class 9. and they form this set X. Instead of always calling the sets A and B, we can give them some other name. Ram, Geeta and Akbar. And in the football team of that school, again from class, I think I said class 9, no, class 11. Does not really matter, but it's given as class 11 here. From that same class, again there are 3 students in the football team. Geeta, David and Ashok. Then we have to find the union of these 2 sets and describe that union set in words. Well, the union of, having seen 2 examples, now we know basically how to write the union. In fact, that is what the union set is. The union of X and Y is this set. Ram, Geeta, won't be able to write it entirely here itself. Akbar, David and Ashok. Okay, now how about writing this set in words without mentioning these actual individuals, without mentioning the names of these actual individuals? Well, we can, one way of writing the set in words is this. The union of X and Y. Well, I haven't written it fully, but you remember what the individuals in X do? They are the students of class 11 in a school who are in the hockey team of that school. Similarly, Y is the set of those students of class 11 in that same school who are in the football team of the school. There will be others also, but from other classes. But from class 11, these are the individuals. So Geeta plays both hockey as well as football. Alright, so another way of looking at the union is this. The union of X and Y is the set of those students of class 11 who are in the hockey team or the football team or both. That is, of course, another way of expressing the idea of union. It is the set of the, instead of saying that it's the set of all the elements of X together with all the elements of Y, we can also say that it is the set of those elements which are either in X, for example Ram, or in Y, for example David, or in both, like Geeta. Okay. Now this somewhat slightly different way of interpreting the union of two sets actually is the way of defining the union. Do not forget that we haven't seen the actual definition of union yet. We are only discussing that initial idea of union. We define it like this. And now comes the definition. The definition is slightly formal. So here's the definition. Let A and B be two sets. The union of A and B is the set. Let us temporarily call it C because it has to be given some name, right? That, or we can write like this, is the set C of all the elements. But now we won't say all the elements of A together with all the elements of B. No, we are going to go somewhat like this. That was a rough way of expressing the union, together with. Is the set C of all the elements that are either in A or in B or in both. So we collect all such elements and that set C is the union. But the question is, why have we suddenly reinterpreted union like this and then presented the definition, although we started differently? That's because we had to address the issue of common elements. You may think, you see, there is a tendency of, in an attempt to write the union of two sets, if there are common elements, if you keep on thinking of the union as, okay, all the elements of A together with all the elements of B, you may accidentally end up repeating elements. In order to prevent that, this is the more careful actual definition where repetition is prevented. That's why we say precisely that C is, which is the union of A and B, is the set of those elements that are either in A only or in B only or in both of them, so that you carefully see that Ram only belongs to X and Akbar only belongs to X, but Gita belongs to both X and Y. Similarly, David and Ashok belong to only Y. So you carefully class the three types of elements, take them together now, and that is the union C. Now we come to the notation. Have I already run out of ink? Oh, I forgot to put ink. Sorry, just give me a moment. Now, just like the addition operation has a symbol, the union also needs a symbol. I mean, how far or for how long can you keep on writing the union of A and B, the union of X and Y? A symbol is devised to write it quickly. and that symbol is this. The union of A and B is denoted by writing this. How is it read? I mean, what will you say when you want to read this? We read this as A union B. You can just say simply that A union B, or there is a very nice way of saying this, A cup B, because this symbol looks like a cup. That is also a legitimate way of reading this, okay? It's not something that I have come up with, no. It is there in the literature, we sometimes say A cup B. Okay, so that's how also you can read the union of two sets. Alright, now if I express this union in the way this notion has been defined here in the actual definition, in set builder notation, can I write like this? That is, for two sets A and B, A union B is the set of all elements X such that X belongs to A or X belongs to B. It seems like, yes, we have got the idea fully here, but there is a problem. Problem with this word or. You see, the union of A and B is the set C of all elements X that are either in A or in B, but or in both. Where is that thing? It's not present here. So actually this should not be the union, provided you are using the ordinary meaning of the English word or, which means either this thing or that thing. In mathematics, however, the word or has a slightly different meaning, a more inclusive meaning. So let me just discuss about that meaning a little bit. Suppose you have two statements. Again, I am going back to those mathematical logic part, okay, which we saw a little bit of while discussing the implication construct. Remember, we defined P implies Q, the meaning of P implies Q using a truth table. And there we also talked about statements themselves. A statement is a sentence which is either true or false. Okay. Now, instead of having the implication in between two statements, simple statements, to have this compound statement, you can also have or, P or Q. Now this also has a truth table for it, but let's not go into that. There is no need to be unnecessarily formal. We just try to see the meaning of or. Ordinarily, when you see something like this in a sentence, normally you think of the sentence like this. It means that either that first thing is true or the second thing is true. And in some cases, we do not mean that both are simultaneously true. It depends entirely on the context. However, in mathematics, we cannot have such ambiguous use of something. We have to define something precisely with one meaning, no ambiguity, and stick to that meaning. In mathematics, OR is inclusive OR. So when we write P or Q, actually the meaning of that is this. Either P is true or Q is true or both are true. This last part, or both are true, is included when we use the word or. So it may look like the ordinary English word or, but everywhere in mathematics where you see or, it means inclusive or. But what is the reason for this? The reason is that inclusive or appears much more frequently than exclusive or, which is what we normally mean when we write an English sentence. When we use or, in most of the cases we mean it's exclusive or, that is either something is true or something else is true, but not both. In maths, however, or means inclusive or. If you want to use exclusive or, then you have to say it separately. Okay. So with this new meaning of or, now this is okay. This means that A union B is the set of those elements that are either in A or in B or in both, because now or means inclusive or. Alright. Now having gone through this much about union, we can also try to draw the Venn diagram of the union of two sets. Alright. So let's do that now. Union of two sets means which two sets? Any two sets. So say you are given two sets A and B, and just for the sake of completeness, we also considered that both of them are subsets of some universal set which is there in the background, say U. So when you draw the Venn diagram of these three sets, of course, again, you draw a rectangle to represent the universal set, whatever it is. And then, inside this rectangle, you draw two regions. One will represent A and the other will represent B. So the rectangle represents the universal set U. Now, one of them represents, I am deliberately drawing somewhat of an irregular region just to show that you can do that. Okay, it's not necessary to always draw a circle, and it's definitely not necessary to try very hard to draw actually a nice circle. That's not needed. Say this region represents A and this region represents B, but what is the reason for this intersection of the two regions? That's because there may be common elements, just like in that example, 2, 4, 6, 8, 6, 8, 10, 12. So 6 and 8 will appear here because those elements are in A as well as in B. So they should lie in the interior of both the regions, representing the sets. However, where are the dots? We cannot write any dot here because our sets A and B are general sets. They can be anything. Okay. So in this case, we do not draw any dots, just the regions. Whatever dots A and B may have, they are inside. Similarly, whatever common dots they may have, they are within this region. This is understood. However, what is the set A union B in this figure? That set is this. In order to show what that set is, in the text you will see that color has been used. The region in the plane which should be the region pictorially representing the set A union B has been drawn turquoise or whatever color the book has used. Here, however, we do not have any, we have only black. So we have to devise some other way of showing what the region that represents the union of A and B is. And what we normally do, because while writing the exam also you won't have color, so we use parallel lines like this. This is the set A union B. It consists of those elements of A which will lie here. Those elements that either lie in A or in B or in both. Okay, so pictorially this is the Venn diagram of the union of two sets A and B, and according to the rule you write A union B beside this set, anywhere outside that region, somewhat close to the region. Alright, now remember that we started the discussion of operations on sets using the examples of operations on numbers that we already know. Now next comes some properties of this operation union of two sets, and alongside I have decided to also show similar properties of operations on numbers. So although we are going to write the heading some properties of union, but I will also have another column for properties of numbers. Let's see what that means. And the analogy of these properties between sets and numbers leads to some interesting notions. We won't discuss those notions because those are higher level things, but it is something interesting. Properties of union. Okay, now because I have already used that part, so why not write properties, the corresponding properties of numbers on this side. So automatically I have two columns. Let A, B and C be any sets. The first property, there is actually no first or second, this is just one of the ways of showing them. It has a name, commutative law. What it says is that when we form the union of two sets, it does not really matter the order in which we take the two sets. That is, whether you write A union B or B union A, they are actually the same set. Number 2, associative law. This one says, this one is not about changing order. We keep the order intact. However, we associate the sets separately, differently. you see the parentheses really mean two different ways of considering this union of three sets, because we haven't really defined the union operation for three sets, it's a binary operation. So we have to unite two sets first, and then with the result we unite another set, and this can be done in one of these two ways if you keep the order intact, A, B and then C. And this law says that no matter which one you choose, you have the same set. So whether you take the union of A and B union C or the union of A union B and C, you get the same set. 3. Identity element. Okay, I think I will run out of space. But anyway, let me just write these three first, and on that side I am going to show the corresponding ones for numbers. A union the empty set is equal to A. If you think about these laws and go back to the definition of union, you will pretty quickly understand why they are true. However, on this side, let A, B and C be any, say, real numbers, and say, like union, on that side we consider the operation of addition of numbers. Now these are some laws with which you are already familiar. They also have the same name. Commutative law. When we add two numbers, the order does not matter. So this is commutative law which pertains to addition of numbers. Similarly, we have associative law or associativity. A plus B plus C is equal to, let me also put parentheses in exactly the same way. How you combine the numbers together, it does not really matter. The end result is the same. Identity element. A plus 0 is equal to A. In a system where you have some objects and an operation which helps you combine two objects of that type and gives you a third object, any element like this which has no effect at all on the other element, so that after doing the operation you get back that other element, this type of elements are called identity element. Identity element. In the universe of sets, as far as union is concerned, the empty set acts as an identity element. In the universe of real numbers, as far as addition is concerned, 0 acts as an identity element. Now, it is rather curious to think of the possible source of these things behaving exactly similarly, but that is not our concern right now. So let's see two more properties here, and let's try to see the corresponding properties on that side. So there is a fourth one. Idempotent law. Just like identity element, there are some elements which are called idempotent elements. In what context, I am not going to say. For now, it's just this law has a name. Okay, let's not go too deep into it. It is just the fact that when you take the union of a set with itself, you get the set itself. Can we think, oh, I think I was using ordinary number, right? Not Roman numerals. Can we think of a corresponding idempotent law here? No, this does not happen generally for numbers. Idempotent law with a question mark. Do we get this for any real number a? No. This happens only when a is equal to 0. So it's not necessary that all the properties of union should be exactly similar to all the properties of addition. Some of them are, but not all. And there is, of course, another one. This one does not really have an accepted name or a generic name or anything like that. You can just call it universal set or universal set law. It does not matter what you call it. These are just, although we are saying these are laws, but these are not anything deep, just some observations. If U is the universal set in your discussion and A is a subset of U, then the union is U. And on that side, let me write here itself. Now, can we think of a number U, a real number U, such that U plus A is equal to U for all A? No. Here also, this works only when A is equal to 0. And when A is 0, U, it can be any number actually. Okay, so let's end the discussion here itself. And we are going to continue with two other operations in the next video. One of them is intersection of two sets and the other is difference of two sets. And besides these two, there is another one, the Cartesian product of two sets, that we will see afterwards, which actually is not available in this chapter, but in the chapter on functions. There is a reason for that. But that's just it for tonight. So, see you in the next video. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.